So what is a extractive text summarization? We have two types of text summarization, extractive and abstractive. And why does your chatbot, your conversational AI need that? Because if we are in a conversation, the chatbot needs to know the context because the next word that your customer in bank is asking may be related to the previous word and also even the previous context, and so forth. And so it should summarize, it should get the overall picture, the big picture of what your customer is talking about. And once, for example, it should be dependent on many sentences before what is already talking about. What is he talking about? And we can classify that as either fake or complaint or it's help. So this is a little bit, this is traditional, but this part, I love this part because it is part of natural language understanding. NLU is a more intelligent way of NLP. So NLP like entity detection, those elementary things. But NLU like question answering, very complex things, reading comprehension, text summarization, all of these are this. That's why NLU is important for me, for Google, for Facebook, for Microsoft. Because it's challenging, it's more related to what human infers about the world. And so let's keep going. Extractive summarization. So as I said, we could have extractive output or abstractive output. In extractive, we just find a subset. For example, you have lots of sentences in your text. We say that, okay, these sentences are enough to represent this text. It has a mutual information with other things that we have ignored for the moment. And it has some correlation with them. We don't like correlation. We want the highest entropy with the minimal amount of sentences. So that's why it's like a robot. But in abstractive, it's a little more challenging because not only we do that, we are also paraphrasing, which makes it more like human. For example, here, Peter and Elizabeth attend, and then they rushed in the hospital. This is a summary. Also, the content could be informative or indicative. Also, your input could be just single document or multiple PDF, for example, multiple articles. You should summarize what the machine learning author wants to talk about machines, and the machines understand that. And my idea is that, okay, I think we should do extractive summarization. It's easier. And then do abstractive. So it's a kind of trick because you do first the easiest part and then you do some paraphrasing or something like that. Of course, humans don't do this, so I think my idea is not natural, it's not good. But I think the simplest naive things that comes to your head could be this. Because extractive is just selecting some sentences that has meaning, there is no redundancy in that. And extractive summarization, so you start with some articles, then you combine it to get a text, you get sentence embedding, vector embedding, and we get vectors. We get similarity if those sentences, for example, these sentences are in this space, those sentences, and then we jump into another idea, because somebody distracts us, and then it's a Markov chain, as I said. So we finally answer a why question. Why he attacked Ukraine? Why is he dangerous? And so maximize semantic volume. We have extractive summarization by maximizing semantic volume. So we don't like something like this because the vectors are in just, the volume is small. We want something like this that has a big volume. You could say this one is not good because it has a small volume. It doesn't represent what we are talking about. But if you know the space and it is as large as possible, it covers all the things. So these points are redundant because it already covers. So this is the idea. And you have traditionally, you have extractive summarization models. You get score of D of I. D is those sentences that we are given, n sentences, and we select just S of them. S is just a subset of D. But we want to keep our length to be less than L. And Y says if it is 1, it is included. It means it is in the is for example, S is, for example, vector 3. If Y is 1, it means that sentence is included. We care about that sentence. We should add it into our basket. And if it is 0, it means that sentence is not in our extractive summary. We should exclude it. And so we want, just like any other idea in machine learning, these are negative. You don't want to have redundant ideas. So yi and yj should be very small. If you have, first of all, they should be 1. Both of them are binary. If both of them are binary, it becomes a positive sentence, which is not good because our score is reduced. So we want one of them at least to be 0, but not, and so we want to increase this relevancy of the sentence I, because we have put sentence I in our portfolio, in our bag, so that should be increased. And because yi should be 1, so it increases because we have take care of that sentence. But it is NP hard, you see. You should watch my playlist about approximation algorithm. I talk about different ways that we can take care of this NP hard problem and solve this problem, at least approximate it. And here, for example, we just need to solve it using exact linear integer linear programming. Integer linear programming, they call it ILP. And the second idea, the mantra says, give high scores for covering more diverse concepts in the summary. So it's like that volume idea that I will explain. But here, we have another binary. We say that it's Z. It says indicating the presence of a bigram in the final selection set. But now we have 2 constraints, 1 and 2. The first one ensures that selecting a sentence implies selecting all of its bigrams. All of these are binary because we are now talking about a different way to, it's combinatorial. It's completely combinatorial. We call it combinatorial optimization. It is traditionally in the context of mathematics and classical, very old computer science. Nowadays, we do it by some other methods. And also, it is just integer programming. And the second constraint, it ensures that selecting a bigram implies selecting at least one of the sentences that contains it. So if M, I, and J is 1, it means that bigram J is in sentence I. Bigram J is in MIJ. If it is 1, then it is in sentence I. And this is the semantic volume. This is a good example because if you just know these red dots, for example, they say just pick 4 out of 7 sentences, then we just need to create this to have a convex hull, and that's enough for the summary, for the extractive summary. Although we have missed 3, but that represent that, because these points are redundant. They don't give us more information. They're just they have some correlations with the red ones. They don't give us many. They don't add to our information entropy. So our volume, as I said, we want a big volume. We don't want such a small volume because many of them are redundant. But here, everything gives new information. It covers all the space that we are talking about. And semantic volume, so there are many choices of this function, and the way we do it is interesting. So we first find a sentence that is the farthest from the cluster. For example, we have a cluster here. Most of the points, most of the sentence embeddings are here, and we have some sentence here. I don't know why the user is talking about something that is far away from the bank context. For example, he or she should ask about, what do I have in my bank account? For example, can you transfer that? And so if we take this, we understand that, for example, maybe he says that I have forgotten my password. So this should be included. And so now this new space is here. It is spanned by this space. So if we have some vectors that are out of this subspace, then we should project it into this space to see how can we add, which one is more important to add. Still, the procedure is the same because we find the farthest point from this space. As you see, we need this distance. We need this to be big distance. And what is your measure? This is your measure distance to a subspace. Because this is our subspace. If you watch my lecture on subspace clustering, you understand these things better, because there we talked about linear algebra, whatever you need to know about these things. So if you have a vector, let's say this one, we want to see which one is closer to this subspace. We just project it, and then we can compute this. So because we are nothing, we should create a clone of ourselves, because if the chatbot can understand your voice, your reasoning, so even if you die, if your girlfriend dies, no problem, you can still talk to her, having a good time, because you can hear what she says, you can copy her voice, the same kind of reasoning as usual, and so you can enjoy. So there is no point in dying. So if people die, you can create a clone, a chatbot that can mimic that. That's why thinking and NLP is important, because if, for example, Putin is not strong, because he thought is not powerful. And so he cannot be a good person like Aristotle or Socrates or Plato. So he cannot help humanity.